Let's study sound waves in this video. What do you think is a wave? You may have thrown something in water and seen waves or ripples produced on the surface of water. In this case, the disturbance travels outward from point of impact. The waves you see are the propagation of energy through the water, but the individual particles of water do not travel with the wave. Depending on the necessity of a medium, we classify the waves in two types: mechanical waves, like our water waves or sound waves, which require a medium for propagation, and electromagnetic waves, like light waves or X-rays, which do not require a medium for propagation. We call the waves which travel continuously in the same direction as progressive waves. In progressive waves, all the particles of medium have the same amplitude, period, and frequency. If the particles of a medium oscillate perpendicular to the direction of propagation of the wave, we call it transverse wave. And if the particles oscillate parallel to the direction of propagation of the wave, we call it longitudinal wave. Let's study the characteristics of transverse waves. In transverse waves, the medium is divided into alternate crests and troughs. The distance between any two successive crests or troughs is called wavelength of the wave. The advancing crests or troughs are responsible for transfer of energy. Transverse waves can be polarized by constraining the vibration of particles in medium. Now the characteristics of longitudinal waves. In longitudinal waves, the medium is divided into alternate compressions and rarefactions. The distance between any two successive compressions or rarefactions is called the wavelength of the wave. The advancing compressions and rarefactions are responsible for energy transfer. Longitudinal waves always require a medium for their propagation. The density and pressure of the medium varies along the path of the longitudinal waves. These waves cannot be polarized due to their basic property that particles vibrate parallel to the direction of propagation of waves. For sound waves, we just need to set any object into vibrations. For example, a vibrating tuning fork compresses and rarefacts the adjacent air, thus propagating the sound waves. What happens when you actually hear is your eardrums vibrate to the frequency of these compressions and rarefactions, and they signal your brain about the sound. Now consider this wave. The maximum displacement of a vibrating particle from its mean position is the wave's amplitude. The distance between two successive particles which are in the same state of vibration is the wavelength of the wave. The time required by a particle to complete one vibration is the period of the wave. Number of such vibrations per second is the frequency of the wave. Frequency of the wave always depends on the source. Newton also gave a formula for the velocity of sound in a medium, where E is the modulus of elasticity and rho is the density of medium. But the velocity by his formula wasn't consistent with the experimental values. So Laplace corrected his formula and gave this equation, where gamma is heat capacity ratio, P is pressure of air, and rho is the density of air. The velocity of sound is directly proportional to the temperature and the humidity of air, but it does not depend on change in pressure in air.